Okay, guys. So what we are going to study is in the next module here. So these topics will not be included in the first exam. All right. So the first exam, just to make sure that we know the scope of our content here is going to be just thermodynamics. All right. All right. Don't worry about what we are studying over here. And it seems like from the poll, so what you have here is the votes are sort of like favoring the Saturday of, I think it's 12, right? 12. Okay, so just want to ask you guys that's already here. You guys okay with Saturday? I mean, if you are here, you can just like voice your concerns or whatever right now. But anyway, if you have like particular reason that you won't be able to make it on Saturday or it's truly inconvenience, then just let me know. I mean, you can do a private message or anything, all right? So I'll be listening and see. But majority, I asked this first section already. The section 1 seems to be all right. So it seems like we're gonna give it a go. Okay. Oh, okay. There are at least 2 confirmed here. All right, and another good thing is because we already decided we are going to release the exam at noon. So it's been 12 o'clock, and then you have 12 hours to work on it. So you have until midnight. So even though you have something that you need to attend to during the afternoon, so I think it's gonna be fine because I would say even though you have like 12 hours to do the exam, but the exam is not going to be harder than usual or anything. It's just going to be like 2 hours exam, just like before. So I'm not gonna like do any acrobatic moves on the question or anything. It's gonna be just like you should be able to get it done like in just normal 2 hours exam. However, having extra times that should release some pressure out of you and sort of like you have time to revise your problems or look it up, or I mean just make sure that you make like your exam paper like golden. Just like perfect A, or ace your exam very easily. All right, so just improve your chance like tremendously. Okay, cool. Okay, so if no objections, then I think the date is set to February 12th. All right, and the exam paper will be released at noon. Okay, and you have 12 hours. Okay, all right, guys. So today's lecture is something sort of like back to your old day, is the mechanics one more time. However, the mechanics that we are about to look at here is going to be like particular type of mechanics. We are looking at something that is periodic in time. So we want to look at the oscillation. So we want some movement that happens over and over and over until you can see like something that periodic happens. Okay. So we are going to discuss today the kind of motion we're going to name it simple harmonic motion, and what is the underlying sort of like infrastructure of everything that's eventually lead you to this simple harmonic motion or the simple oscillation over here. Sounds cool? All right. So I'm telling you guys, today is going to be like a breeze here. It's like there's nothing going on. Like you just like sit back and relax, doing nothing. Is you don't even have like numerical calculations or anything. It's going to be purely like theory. However, there's a key thing. There may actually a couple of key things that you're supposed to be able to pick up today. And it's going to be a good stuff that eventually lead you to understand waves better next time. Okay, sounds like a plan. Okay, and once we have that, the next time we're going to be able to dive into waves story, and eventually we're gonna give you some examples of waves, what kind of waves that you can look at it physically, and then you have some properties that you can calculate. Okay, sounds cool. All right, so let's get started. And what is it? I'm just gonna ask you like a very simple question, and I think this is a question that you have already sort of faced before. You have a simple like mechanical system like this one. Okay, so you have mass and a spring. So the spring is attached to the mass, and then on the other side it's attached to the wall. And then once again, of course, when everything is in equilibrium, spring exerts no force on the mass. Then you move the mass to your right a little bit and then let it go. Everyone knows it's going to go back and forth, back and forth, back and forth forever, right? Okay, and everyone still remember this one. You know that every time you talk about the springs, you have Hooke's law right there. F equal to kx. However, just to make sure that you get things correctly in the vector format, if I write sort of vector format over here, you will have a negative sign right there. Does that make sense to you guys? Okay. That negative sign is just to indicate that when the mass is in the positive x direction, so that means your displacement is positive, then the force that you have over here is going to point in the opposite direction. Make sense? All right. It's my green arrow here and the blue arrow in the figure are exactly the same thing. Just rewrite it. Okay. So just to double check over here, when the mass is at zero displacement, you get zero spring force. That's fine. But then when the mass moves to your left, then now your displacement vector point to your left. So that means what you have for the force is going to be the force that pointing to your right. Cool. All right. And what you saw this one before is just the simple Hooke's law saying that the spring is always exert the force opposite to the displacements all the time. Now, my simple question that I was mentioned about is, can you guys give me the equation of motion of this mass? That's it, guys. Just kidding. Just write me the equation of motion of this mass. When I say equation of motion means I just asking you to figure out the equation that eventually going to tell you what is going to happen with this mass in time. So it means once you have the equation of motion, and if you know exactly what is the solution of that equation, then that means you will be able to predict, or you can even pinpoint what should happen to the mass at later time. Because the solution of that equation will tell the fate of this mass. Where should it go? Where should it move? Where should it be? Everything. So the importance of equation of motion is once you set it up, and if you can figure out the solution will be the future of this mass. All right, it's not the future of this mass, but that's the deterministic property of the equation of motion. How do you get equation of motion? Of course, you go back to the Newton's second law, sigma F equal to ma. That's it. That's the starting point of everything in mechanics, right there, back in physics 101. So what I'm doing over here is, okay, John, I'm just going to do like a free body diagram. So think about it. If you are only focusing, oh, whoa, this is big. If you're just focusing on just this mass alone, that's your body. Okay. So you say, okay, what kind of force acting on this mass? You say, okay, John, because we assume at this point that the floor doesn't have any friction. So the only force that acting on this mass is going to be that spring force, the F sub S right there. And that's it. Sigma F is going to be that kx. However, even though you look at this one, you can see that it's a single dimension problem because the mass is M is going to oscillate along the X direction. But no matter what is the vector equation, don't forget that. So even though you tend to like kx, but then you don't forget that you have to put the negative sign there because it's a vector, it's a negative x, right? Okay, even though it's one dimension, you don't have arrow on top, but this equation is still a vector equation. Okay, so you say negative kx equal to ma, and then I can put subscript x there just to say, hey, everything is along the x-axis. So far, so good. Okay.
Okay.
Now, everyone knows that the acceleration is the second derivative of displacement. So that means what I can do is I can just write this one as the d2x by dt2. Yes. Okay. So that means if you rearrange things and then just put the acceleration on your left-hand side, then you equate that to the right-hand side, then you move the m to the opposite side, you have a negative k over mx. So this is what you get right there. I put this like a one-star equation right here. So it's d2x by dt2 equal to negative k over mx. Question, can you solve this differential equation? What do you think? Can you solve this one? And everyone can see this. This is the second order differential equation because it contains the second derivatives in this equation. All right. You probably like now bring you guys back to calculus 2. You guys did calculus 2 already, I guess. Yes. Maybe. All right. My question, do you know how to solve this? If you know, that's it. This lecture is done. There's nothing else to it. The main goal of this one in today's lecture is solving this kind of equation. I am taking calculus right now. Okay, don't worry. I'm just asking you, just teasing you guys. No, we don't need that. We don't need that calculus 2 at this point. So what I'm going to do, and I'm going to show you how to think about this one. And I hope by having this done, then you're going to be able to solve this kind of thing. All right, I think I need like a couple of pages here. All right, so let me write everything one more time here. And I'm going to ask you this question. Let's start from something simple first. Okay, so let's start from d2x by dt to equal to negative x. Okay, just that. And even better about that, it's kind of annoys me. All right, let me just give you just this. What do you see? Just kidding. What do you see right here? So if you don't want to go through like the techniques that you use in like solving the second order differential equation on and on, what you're seeing over here is you would like to figure out the x that once you get differentiated twice, then you get the original function or the original variable back. Does that make sense? That's what you want to figure out. What kind of function x, as a function of t, of course, will eventually give you back the original function once you get differentiated twice. Now, you think back for the whole, mathematics that you have learned since you was born or whatever, what kind of functions you are facing since like, elementary schools, whatever. So they're actually not a lot if you think carefully. And this is something very amazing about mathematics in our world over here. You only learn about power functions. So when you say power function, that include everything x, x squared, x cubed, square root of x, 1 over x, everything. That's a power function. Let me classify that as power functions. Second is trigonometry function, sine, cosine, on and on. Yeah. Third one is exponential function. You do like, power. I mean, not power is like, but now your variable is on the exponents there. So you do like 2 to the x, 3 to the x, or e to the x. And the fourth one is the inverse of that exponential is logarithmic function. Isn't that amazing? That's it. That's all you learn. Wow. And there was a reason for it, why you only like learn a couple of functions mainly. But then, of course, you probably have heard, like, I mean, not have heard, you probably have used like absolute functions or crazy, some manipulated sort of, functions on and on. But basic functions, fundamental functions are pretty much power, trigonometry, exponential, and logarithm. And the reason for that is because think about this. If you say about Ajahn, could x be like, power function, like 2t cubed plus t squared on and on? This won't work. The reason for that is because once you take derivative, the power just keep disappearing on you. See this? Right? You won't be able to get the original x back once you get differentiated twice. So that means this class of function won't be your solution. Power function won't qualify. Does that make sense? Okay.
Okay.
Get the clue. And then you just like, okay, then what about, let me try like, trigonometry function. So you say if x is like sine t, you differentiate one to get cosine of t. Everyone still remember how to differentiate sine and cosine, yeah? And you do the second derivative of that, you get negative sine t. No, the original is x, but what you get is negative of the original. So no, this one not good. Okay, and then you keep going. You just like, okay, now what about exponential? Let's do base e because that's easy to differentiate. And you still remember from calculus 1 that the good thing about e base is just every time you do the differentiation, you get back the original. And this one works. That's it. This is what you want. So at least every time you see this kind of equation, you can assume that your solution must be some sort of like exponential function. Does that make sense to you?
Okay.
I hope if you have a chance to take like calculus, or not calculus, if you have a chance to take like physics 3, which probably they don't have, but anyway, if you have a chance to take like, quantum physics on and on, there will be some more second order differential equation for you to solve. And this whole thing will just come back and haunt you again. Okay, what about logarithm, Majan? You forgot about the logarithm. Logarithm doesn't work because when you take the derivative, it turns into 1 over x, and that's it. It's fall into the category of power function anyway. You won't be able to get the original function back. Does that make sense? Okay. All right. Oh. All right, guys. Thank you for the comments. Okay, your friend just asked me, Achan, it's supposed to have number 2 right here. You're right. You're right.
Okay.
Thank you. I just want to see like you guys still, pay attention to my lecture or not. Sorry, it's totally my fault. Sorry, guys. So they're supposed to have number 2 right there. Thank you for that. Okay. All right. So that is the conclusion of this solution right here. It's just like, okay, Ajahn, I mean, if you have this equation, you should have exponential to be part of your solution. But then no, what we have right here, even just a tiny difference, you just have that extra negative sign in front of x. That changes everything. Because now once you have this negative sign, that exponential e to the x won't it won't be qualified as a solution anymore. But what is going to be the solution? Yeah, right there, guys. So x supposed to be like in the family of sine function. And then when you do x prime, you get, I'll do it one more time here. X double prime, perfect. That's what it is. That's good. And then you say, but then wait, why you have to, why you favor sine? Why don't you want to start with the cosine? I don't mind. You can do with the cosine too, because it has the same property. When you take derivative of cosine, you get sine of t. You do it twice, you get negative cosine t. That is still perfect. You get negative of the original back. So in conclusion, both sine and cosine can be your solution. And if you sort of vaguely remember from calculus 2, I mean, if you already faced part of this, but if not, that's all right. The idea is if you already figure out that cosine is good, the sine is good, cosine is also good, then the combination of the two will also be good. So what I can say is, all right, now you have freedom to pick. You can choose either sine or cosine. But even better, that sine and cosine are actually the same thing, right? Because when you have the sine function and then you slide the sine a little bit and you get the cosine, then you slide your cosine function a little bit, you get back the sine. So to me, sine and cosine are pretty much the same thing with, a little bit of, displacement and on and on. But that's not all. We have some more things to do. But is that it, Ajahn? You have only like sine of t that works. The answer is not necessary. You can actually manipulate this one a bit further if you multiply the that sine or cosine by a constant in the front. Okay, follow me what happened. You do the derivative here, you get a cosine t. You do the second derivative there, you get negative a sine t. And once again, you facing that original a sine t again. It works. So that means you can also introduce some constant factor in front of your function. It won't change anything. The reason that this one works because once again, this differential equation is just a linear equation. So that means it doesn't matter. I can multiply a across this function and nothing is going to change. So that's the reason, the same thing, that a can be pretty much put it in your solution as well. Does that make sense to you? All right, so it doesn't, it's no big deal. I can actually add some extra constants to it. It won't change anything. It's still qualified to be solution of this equation. Nice. What else can I do? Actually, I can even do this. Well, Ajahn, what about instead of multiplying, can I add something to the parameter or the variable that we're dealing with? Let's try. If I put some, constants add on top of that variable t, would that change anything? You do the first derivative, a is there, derivative of sine is cosine, and then you do the chain rule. Remember the chain rule, right? But then once you do the chain rule, you can see that when you add just any numbers or constants to the variable, it doesn't give you anything extra. That is perfectly fine. So this derivative give you 1. So you do it one more time. You get a derivative of cosine is negative sine. And the chain rule will give you 1 again. So that works. Even you add some constant to the t, that is still classifying as your solution. So is there anything else that you can manipulate? It seems like that's it. When you're dealing with the linear type equation over there, you can either multiply by constant, that's still fine. You can add a constant to your variable, that is also fine. So the whole form of this one should give you your general solution to this equation right there.
Okay.
I don't know, I'm like talking too long for this, but I know maybe something that you have already known before, but I hope this give you an idea or some connections to, you know, ordinary differential equation that you probably have seen it somewhere. Okay. Oh, there's a question here. Why do we want second derivative of x to be the negative x? Because this one eventually is going to link back to here. My original equation, don't forget. I still want to go back to our lecture right here. So because I noticed that in our equation, there is a negative sign here. So I hope that by knowing that characters that we just learned, we will be able to solve this equation. All right. Thank you for your question. And that's exactly where I want to be. How can we solve this one now, guys? Come on. How can we solve this equation now? Do you know what should be the solution of this equation now? Once we learn this. Thank you for the question, though. That's perfect timing. But now did I answer your question there? Yeah. The reason I want the negative x because that is the form of the equation that we want to solve right here, which came from the equation of motion, which came from Newton's second law. Perfect. There you go. All right. So the reason that we need that negative x because of Newton. Okay. Now, do you know how to solve this one now? Well, Ajahn, there is some problem here. This is annoying. There is an extra terms in the front. It's k over m, right? Even though it looks annoying, but it's important because k is a spring constant, m is the mass of the system. So to do this, that's still not bad. Come back to our, things that we learned over here now. Let's start from this again. Look at this, guys. If I have x to be, a function of t, right? A sine t. Every time I do derivative, it's fine. It's a cosine t. Okay, I'll just keep writing. Okay. But then, how can you have a factor in the front? You want something popping out in the front. A is going to be there. It won't change anything because it's just a fixed constant that show up in the front all the time. So let's consider this. What about if your function looks like this? Let me give you some extra terms in the front there. Let me call like, some small a. Okay, so now you have capital A and then a small a like that. So every time you do the derivative, all right, of course you do a cosine at, but then don't forget the chain rule. You should have to follow up with the derivative of that at by dt. And this derivative will give you a. With me, guys? So that means once you have some factor multiplying your variable, when you do the derivative, that factor will show up in the front. Cool? Start seeing something here. But then you do the second order. So you do it one more time. So you differentiate the last expression one more time. A, mini a, big A stays there. Derivative of cosine is negative sign. But then you do the chain rule one more time. That chain rule give you extra a. So that means at the end, after second derivatives, you're going to get negative a, the mini a square, followed by the a and sine at. Cool?
Okay.
So from the look of it, the way that you will be able to have something extra popping out is going to be the square of something over here that show up in the front. That correlate to the parameter that shows up in front of your variable. So that means, come back here. If you would like that k over m to pop out, that k over m must be square of something. Does that make sense now? It must be square of something. So let me introduce to you that root k over m, and then just make things a little bit shorter to write. Let's call this root k over m the omega. Does that sound familiar now? All right, but anyway, your differential equation will look like this double star equation over here. So now your equation will look like d2x by dt2 equal to negative omega square x. And with this, do you know the final answer now, guys? Yes, yes. So in conclusion, once we know this is good, your general solution will look something like this. Let me write it out for you guys. It's going to be any constant in the front. You can pick and choose sine or cosines, up to you. Then you just put the omega in front of your parameter t. And then because you allow to add any constant to it, just add some number to it. That is it, guys.
Okay.
This is the solution of this differential equation. And this will tell exactly what will happen to this mass at any time t. And can you see the sort of like the beauty of this whole thing here? And this is why the Newton's law is so powerful right here, because actually you started out just only from sigma f equal to ma. And once you have this, you get down to this equation there. And once you have that, here, this is your solution. The solution says this mass is supposed to go back and forth in sinusoidal manner. It's going to follow sine function or cosine function. They are the same thing. So that means you are going to get the oscillation out of this system, and you are done.
Okay.
All right, but I find this one is very, fascinating. That, I mean, just a simple equation of motion, then you unlock the future of this mass, pretty much. Yeah, this mass has the fate is here. It's being governed by sinusoidal function, and then you plug in the t, you know exactly where this mass is supposed to be at any time. Cool. All right, so I hope, I mean, my long introduction, half an hour or whatever, this will give you the whole idea of how to solve the second order differential equation. So let's dive into a little bit, in terms of the interpretation of what those parameters that we introduced to this solution means. This is it. So let's say if I pick a cosine omega t, that's fine. Okay, about that, this is good. So if you look at this one alone, you guys know that the cosine function will never go above 1 and never go below 1. So this means the value of the cosine function will run from -1 to +1 all the time. And that means your x function will be somewhere between +a and -a at all time. You guys with me? So that means that capital A that we introduced to you give you the maximum displacements possible for this travel, for this translation. And that's why you're seeing that a and -a to be the cap, or this, I mean, the maximum and minimum possible value. Okay. And second thing, what about the omega, John? The reason that we pick omega because of this. You look at this one. Let me ask you, what is the unit of omega? You probably have seen this before, John. Wait a second. Omega is multiplying with the t, but the t is already in second over here. So that means the omega must have the 1/2 unit, because everything that is inside sine or cosine function or any transcendental function, logarithm, exponential, must have no units. You guys with me? Okay, just to emphasize this point one more time, because this one is so good in the sense that you're supposed to be able to, have this in the back of your mind all the time. You have never seen this before. For example, you never seen a sine of mg. This This is like, I would say, illegal, because sine of mg, this is going to be super weird because mg has a unit of Newton, that's the force. Sine of Newton, that's going to be like what? Okay. So what you have over here is everything that follow up sine, cosine, log, exponential must have no units. Okay. All right. Very good. Some of you say about time, what about radian? Think about the radian. The radian is the angle in the SI system. But the way that you calculate the angle is by the arc length divided by the radius, right? Okay. But the arc length has a unit of meter. It's the length. And the radius is also has a unit of meter. So actually theta has no unit. So this is the reason why it's fine for you to have sine theta, and this one won't work because the theta itself is just a number. It just gives you like, okay, all right, I know if you go complete 2 pi, then you complete 1 cycle and then you're done. Okay, does that make sense? So that means the omega must have the 1/2 units. But then everyone also know that if you take omega t to be 2 pi, this argument right here will take the whole function and cycle through 1 full circle, right? So that means this whole thing will complete 1 oscillation, 1 cycle, 1, I don't know, you say it's complete 1 round. So you call the time that it takes 1 round is 1 period. You use capital T for that. You remember this from circular motion, maybe? When you move things in circle and then we complete 1 complete cycle, you call that time that it takes of 1 period. So that means every time that you take t to be 1 period, the omega t will be 2 pi. So that means you know exactly that the omega itself is 2 pi over period. And this formula looks so familiar to you guys, right?
Okay.
Yeah. So it turns out the omega itself is the angular frequency or angular velocity that you had seen before. And that's the reason why we picked omega to be the name of the square root k over m. So in conclusion, the actual unit for the omega, even though it say 1/2, but it's actually is a radian per second, because the radian itself has no units, but it just is the numbers in talking about the angle in the units of radian, right? Which is you have an alternative unit, which is degree, 360. Okay, that's just, back in the day, we just decided to divide a circle into 360 parts and on and on. But over here, that's in radian. And because you already remember that, okay, Ajahn, if you know the period, the inverse of the period will give you the frequency. So that means you can also pair this omega with the 2 pi f, exactly the same formula as you saw before. Okay, so that's it, guys. So that means if you're starting from here and then you compare what is going on when you complete 1 full cycle over there, the time that it takes over here is going to be 1 complete period right there. Okay, cool. All right, so I hope this sort of like review things that you have already seen before. Next, what is going on with that extra constant that you add behind that omega t? Because we just said you can always be able to add some constant, into your variable, and then just things that happen is just shifting things, but it won't change anything in terms of the solution of the whole differential equation, right? But what happens when you really add some numbers to it? So think about this one, John. It's not bad, because all you need to know is just like you want to pick something out of this one when time is equal to 0. You see what I'm saying here? So think about this. If I say, hey, guys, let's substitute time equal to 0 in there, what you have left is just going to be that dude, that phi over there that's sitting there. And it's just saying that, hey, at time 0, I am here. I am at the angle phi right there. So what this phi means, we're going to name this one. Well, we don't want to use the word angle. So actually, even though you think of this one as an angle, but because we associate angle with geometry mainly, so we're going to just like, okay, just forget about this name. Let's call it phase.
Okay.
Introducing phase, but in the back of your mind, it's pretty much the same thing as angle. But what does it mean by phase? It's just like, okay, it's just like angle with some utility in waves. Think about this. So when we have this one complete cycle, everyone still remember is 2 pi, right? We just did that. So that means if you divide this in half, so this is going to be the location that indicate that this is pi, right? And you can keep dividing this. All right, I can do like here, and this is pi over 2. You can do it there. This is 3 pi and a half, right? Everything's good. So what I'm saying over here is that means if you look at each particular point on this curve here, so you can say, okay, Dan, the first blue dot over there, that's pi over 2. The second blue dot, that's pi. The third blue dot, that's 3 pi over 2. The last blue dot, that's 2 pi, right? So that's what it is. So that means actually you can associate each position on this curve with an angle that we name phase. So that's why we name the phase, because that will allow you to particularly mention where on this curve you're talking about. And let's assume that, hey, that phi is just sitting right there. So what I'm saying over here is every time that you add that extra phi into your expression, it means you want to start this curve when it's sitting at angle of phase phi. That's why we name this is the initial phase. Initial phase. So think of it as like it's a phase at the starting point, or actually more, it's not more, but I mean, it's maybe official name is a phase constant. Because sometimes you might mean that you want to translate your wave to your left a little bit, something like that, with that constant of phase. Okay, so this is the reason why if that point that you're looking at is phase phi, no doubt the curve of the bottom curve here that I highlighting blue over here is going to start right there. See that? You guys? There. That's where the phi is. Same phi that you're looking at up top right there. I'm highlighting blue. Okay, so I hope this one give you some, introduction of the mathematical description of the solution of Newton's law that we obtained from mass on spring. Does that make sense a little bit? Okay, so I hope this give you a general form of the sinusoidal function, which turns out to be the solution of the Newton's law, which characterize the motion that is periodic in time. Let's go back and forth, back and forth, back and forth. So you're getting some oscillation going on. And because now you can see that everything is governed by that omega. The omega give you how fast, right? Because that is your frequency, or it will give you the period. So once you know the omega, you know exactly how frequent this thing is going to oscillate back and forth. And because you only have this parameter to talk about your oscillation, that's why we name this simple. Simple, because you have single frequency. Simple harmonic motion, SHM, and you are done. Okay, so anything that's oscillated back and forth with a specific value of frequency, and there's a single value there, and can be described using sinusoidal function, that is your simple harmonic motion, guys. Okay, so I think that's the introduction that we have for you guys today. After the break, we'll look into, some detail that we can extract from it, and then eventually we are going to take a look at other system that eventually is going to have exact same characteristics. And you will see that when you understand everything that we have learned since the beginning of today's lecture, the rest will be just like piece of cake.
Okay.
All right, guys. See you after the break. We'll take 10, yeah? Hear me? Forgot to turn on the mic. Sorry. Okay, let's start over again. Okay, thank you for telling me. Otherwise, then I'll be talking. Like,
Okay.
All right. So once we already seen that everything from the equation of motion give you the solution, and now we understand the shape of the solution to the equation of motion in the case of mass on a spring, then we will be able to calculate anything that you want. Okay, velocity, acceleration is going to be simple because now you know exactly where the mass should be at any time. So if you want to figure out the speed, I mean, better velocity, okay, so that means all you need to do is just take derivative of the x with respect to time once. And you are going to get, all right, I pick cosine, okay, but now you understand sine and cosine are exactly the same. So from now on, when you read the textbook, and then some textbooks say the solution of, or oscillation motion is described by a sine omega t plus phi, you will say the same thing. It's just your preference, okay? So if I pick cosine, then derivative of cosine is the negative right there. And then sine omega t, don't forget the chain rule will give you extra omega. So what you get in the front, that omega a right there, it's going to be maximum possible value of the velocity that you're going to get. Just like a was the maximum displacement that you are going to get. Same thing with this. So that's why you can draw the conclusion that the omega L will be your maximum speed or velocity magnitude. Yeah, cool. All right. And if you want to do one more time, you differentiate that velocity again, you will get the acceleration. And the derivative of cosine, you get derivative of sine, you get cosine. The negative sign stay there. Chain rule will give you extra omega. So you get omega square in the front. So you guys follow here, right? There you go. And once again, the interpretation is it going to be exactly the same. Whatever comes in the front of sine or cosine will give you the maximum value possible. So you are saying that the maximum acceleration of this oscillation will be omega square A, and you are done. So this will give you the complete picture of what is going on with the mass on the spring oscillations. It's a simple harmonic motion with omega. Okay, I think I forgot to put it here. It's nice to have it here. Omega is square root K over M, just to remind you. Okay, cool.
Okay.
Very good. So far, so good. Just let me know if you have any questions there. Okay. All right, here we go. Now it's your turn. Let's say if we analyzing other system, not mass on a spring anymore, but it's a simple pendulum. So you have a pendulum means you have a mass is being attached by a spring, by a string. And then, of course, at equilibrium, the mass is just hanging vertically. But then if you displace the mass out from the equilibrium position a little bit and let it go, this is going to swing back and forth. Everyone knows this. All right. And you already even studied this, I think, back in the maybe, high school physics on and on. But we are going to use the same principle that we just developed with that mass on spring and do it again right here and see the similarity between the two. And you will, you see that, okay, the mathematics underlying these two systems are exactly the same. Give it a shot, guys. What is the equation of motion of this pendulum right here? Can you give me that? Well, Adan, just look at your slide right there. It's already there. All right. I want you to be able to write that one down. Okay. Just write this equation for me. Can you, starting from the diagram or whatever you have, can you write that equation of motion that show up already on the slide? So first thing first, everyone knows that this is the movement that's going along the, circumference of a circle. Think of it that way, right? It's going back and forth right there. So one way that you can do this is just give like a guideline over here that will help a bit. So let me draw this line over here. So this is pretty much the direction that the mass is traveling at one particular time. So like if you just considering like a short amount of time, it's just like the mass is sliding on the inclined plane. Think of it that way, right? Because the mass is going to travel in the tangential direction to the curve of motion. Okay, cool. All right. Second thing is, once you set that one down, all you need is just another reference that go perpendicular to this. So you can imagine that, okay, so you can think of the coordinate system that we are going to use is going to be that green coordinate system right there. Whatever vector that doesn't point along our coordinate system, you just decompose them and put them in the right direction. So let me highlight this one more time. If my mg is down here, it's not pointing along our coordinates there. I'm going to split this into two components, one going in. All right. One going in, and I say the reason I quiet because I didn't call this one any angle just yet, but any name just yet, but you can call this like a tangential direction. And you can call this one like a perpendicular direction if you want to. Okay. Or you can call it like a radial direction. Okay. But once you have this, then your original is gone. You just decompose the original mg into two components, tangential components and the perpendicular components. Okay. The tension, it's fine. You don't need to do anything because tensions point in the perpendicular direction already. And from the look of it, because the mass is going to move up or down along the perpendicular direction. So now you know right away that, of course, this will cancel out with this. The tension will cancel the mg cosine theta. And that is the equation along the perpendicular axis, T equal to mg cosine, T equal to mg cosine theta. But that one, we don't need. All right, we just, okay, that's fine, then that's good. T must be equal to mg cosine theta. All right, but now what happened to the mg sine theta? So you might be able to use, it's a vector equation anyway. You cannot avoid symbol in the front. So you might be able to say, hey, on this direction over here, that's a positive direction. This direction is going to go negative, right? Don't forget, it's a vector equation anyway. So that means your mg sine theta vector is pointing in the negative direction. Cool. And what about your displacement? Even though it's along the curve, okay, but at an instant, you say that, Ojan, it's already traveled along this curve right here. Here, this curve right there, you call it S, which is fine. Okay, so what you're having is saying that it's going in that direction. So if, let me put an arrow on here, if it's going to your right hand side over there, that is your positive direction there. And because S is just, think of it, it's just a tangential displacement, right? It's a displacement along the circumference of a circle. So it's always in a tangential direction. So perfect. So what you have over here is you can calculate or write down the Newton's law, sigma F equal to MA, that is going on along the tangential direction. You guys with me so far? Okay, so all you need to do is just apply sigma F equal to MA, but the subscript T over there just indicating that, hey, all right, we're going to do it along the tangential direction, not other directions, okay? All right, so with that, so what you have over here for you guys is just execute it. So you say the total force you will have over here is the negative mg sine theta, because mg sine theta is pointing backward in the negative x direction. And then you also say, well, Ajahn, that acceleration is just going to be the second derivative of the displacement. So because we already said that is the s, the arc length along that tangential direction. So you just put it into this equation right there. All right, one thing that you can notice right away, m cancel. So m just disappears. Guys, can you manipulate this one and make it look just like what we just did? Well, Ajahn, of course, you can do it. You can do it. Yeah, I'm doing it right now. Okay, so I just move everything to another side and we'll just keep the second derivative of s on the left-hand side. So it's going to look like this. Oh, not yet. Well, sorry, negative. Okay, there you go. There. Alrighty. How do you feel? Can you solve this equation? It's a little challenging, but can you do it? Pretty much. But no, Ajahn, You have S and you have sine theta. They are pretty much different thing, right? They're not the same. Okay. So what you have over here is just like, no, not gonna work. Except, is there a way that you can change the sine theta into something of S? Or you can change S into something of sine theta. These are the two things that you should be able to do. So when you look at this one, Bajan, that's not too bad. Something is sort of like, we can work things out here. So if you look into this portion of a circle over here, see that? So you will see that you can draw a connection between S and theta. Yeah, why not? Right? Because what you can see over here is you have the relationship between S and theta. Always, theta is just an arc length over the radius. So that means you can always write S as a product between the angle theta, that subtending angle theta, and the radius all the time. So yeah, I'm going to be able to replace this S with the theta L. And the equation now will look like, okay, I can keep theta there. The L just there by dt2. Cool. Almost cool. I can move L to the right-hand side. So that means, all right, I'll just, oh, maybe it's too big. There you go. I'll just remove that one and I just transfer it to the right side. Almost. Except that annoying sine function. You're probably witching right now, like, oh, if that sine disappear, you will get this star equation here. And it looks exactly just like what we did with the mass on spring. And your life will be beautiful there.
Okay.
But right now it's not. But then at least now you can see that, okay, that's your equation of motion. At least you're done. Your job about writing down the equation of motion is done. Except now you want to be able to solve this equation as well. So here comes the approximation, guys. So if you, I don't know if you remember this back in the day of high school physics or whatever, and when every time you talk about the oscillation, you probably heard of that. The oscillation is supposed to happen at a very small angle. The reason for that is this. If you see, if the degree of oscillation is pretty small, like 1, 2, 3 degree, the angle in radian and the sine of that angle, see the numbers? So the error between the actual theta and the sine of the theta will have like very, very minimal error. The difference is almost like negligible. And you can do up to like 5%, your error is still within like 0.1%. So if you want to go up to 10 degree, yeah, it's less than 1% error is acceptable. So this is the reason why, as long as your oscillation is kind of small, okay, bow, not too large, then you can use the approximation. Hey, well, guys, this can be approximated to be just theta when theta is small. Cool?
Okay.
And once you have that, do you see what I see over here? This is it, guys. You got your equation of motion after the approximation to look like, once again, the second order differential equation, but with the structure that you have already known, solution. First thing first, Bajan, I can tell you right away, whatever comes in the middle over here, that is your omega square. So that means you know right away, the oscillation that is happening in the simple pendulum over here is going to give you the angular frequency of square root G over L. So the nice thing about this one is it tells you exactly how to change the frequency of your oscillation, right?
Okay.
Because the only way that you can change how, frequent this thing is going to oscillate back and forth, you're going to have to change either the G, the gravitational field, which means you have to, do the experiment at some other planets or whatever, changing the G, or at least changing the elevation or whatever, or you just change the length of the string that you use in your experiments. So this is the reason why, as long as you're staying fixed value in G and the fixed length of the string, no matter how you're going to oscillate, you're going to push, pull, whatever, it's going to oscillate with exactly the same period of motion or frequency of motion. And that's when you use this one as like a clock, you know, like a pendulum clock, because the period of oscillation is very constant. Cool. All right. Second thing is I can even write down the solution for you guys. You don't even have to doing any, you know, calculus or differential equation, solving anything. It's already in the form of the simple harmonic. I can tell you the solution of this one is going to be A, some amplitude of motion, sine or cosine, you pick, omega t plus phi, and you are done.
Okay.
See how easy it is? Okay, so you know exactly which angle this mass is supposed to be at any time. Okay, by specifying the magnitude of the displacement maximum, that is your highest angle that you want to start with. Omega is going to be equal to square root g over L all the time. And the rest is just, you know, follow the same old thing. Cool. All right. So this give you need the basic stuff that allow you to actually treat any simple harmonic motion of any system. As long as you can keep the form of your equation that you want to solve look like this, you will be able to always evaluate the omega. It's just the square root of whatever parameter that show up in front of that parameter, of that variable, sorry, in front of that variable that you want to figure out. Cool. All right. I just keep saying cool, but it's not going to be super cool if you can do it yourself. Let's do it one more, guys. Solve this one. All right. And that will complete the three system that we would like to study, and will pretty much, like, you know, confirm that you understand the basic structure of the simple harmonic motion and the equation of motion that give rise to that simple harmonic motion. Guys, write down the equation of motion if you have an extended mass. So now the mass is not a point mass anymore. Okay. You have an extended mass, uniformly distributed, let's say, but it doesn't really matter. Let's say you can know, you can evaluate the center of mass. So there's a point that, you know, be your representative of the whole mass. But then once again, you hang this mass on the wall, it's going to fall perpendicularly, vertically, normally, and then you displace it away from the equilibrium a little bit, let it go, it's going to swing back and forth, right? Right? Okay, that's no problem. I want the equation of motion, guys. This is going to be fun.
Okay.
So remember the rotational motion that you study is like a second Newton's law for rotation, something like that. Okay, I think you guys remember this. All right, guys, give me the equation of motion. I'll give you like a quick reminder over here. What you used before was like, here we go. Total torque equal to the I alpha. Is it good? All right, when you have an extended mass, you're not talking about the mass anymore. You are talking about the moment of inertia. Yeah. Okay, very cool. All right, so with that moment of inertia there, then you just evaluate the amount of total torque that's going to twist this whole mass over here and then give the turn to the whole thing. What is the torque that is applying to this mass? So if the pivot is at point O, the weight of this mass is going to be the one that is applying the torque to the whole system. Make sense? All right. And everyone knows how to calculate the torque. The magnitude of the torque is just R. Right, you do the cross vector, right? It's just a magnitude of the cross vector between vector R and the vector F. But because right now you only care about the magnitude, it's just RF sine theta. Or you might sort of recall the form of this equation is like, it's the product between the force and the direction from the line of force to the point of rotation or the pivot point. Sort of get that somewhere, somehow. All right. So what I'm saying over here is all you care about is just, okay, look at the line of force. So the line of force is here. That's the line of force is along the green line right there. And you want to measure the distance from this line of force to the pivot point. Every time that you want to talk about the distance, usually you have to measure perpendicularly. So you want to measure the distance at perpendicular to this line of force right there. Okay, remember that one? So this is your R perpendicular. So that's your distance from the line of force. Or sometimes you might refer to this one as a lever arm or something like that. Okay, แขนของแรง something like that. Okay, all right, so with that, then you know, okay, Ajahn, if the distance from the pivot point to the center of mass is D, that R perpendicular right there is the D sine theta. Cool. So that means your torque is going to be just an mg, because that's the only thing that's applying the torque to the system is the weight of the mass, and followed by the D sine theta. That is your torque magnitude. Cool. All right. You get the magnitude of torque. But then what you have over here is what's next. So what you have next is you have to recognize the direction of this torque. Don't forget, this equation is a vector equation. I want to emphasize this time and time again, that don't forget the Newton's law give you the equations that is a vector in nature, right? You need the direction. So think about this. This torque is mg, is trying to pull the mass down in this direction. It's a clockwise direction. So remember, every time we talk about rotation, we use the right hand rule. So you just use your forefinger, wrap your finger around the rotation direction, then your thumb is point into the page. So that means this torque is applying into the page. It's trying to twist this mass clockwise. Cool. But then, because when you displace this mass, the equilibrium point is supposed to be like in the vertical line, but then you displace to the right. So it at this angle theta, you already displaced here in this direction. So let me draw the vertical line over here. That is your equilibrium point, that blue dash line over there. So when you rotate your CM away from that blue dash line to your right, your angle is pointing clockwise. See this? And when you use your right hand, curl your forefinger along that counterclockwise direction, your thumb point to your face. So that means your theta right here is pointing to your face. Yes? And if you want to call something point to your face to be positive, so that means the torque that you're seeing over there is going to give you a negative torque direction. Or you can call it like a positive Z if you like. Okay, so that's why there is a negative sign in front of the mgd sine theta. So the net torque acting on this mass is negative mgd sine theta. Cool. Equate that to the I, the moment of inertia of this torque, and the acceleration that you get from here is just the second derivative of the angle. That's the angular motion that you learned before from, angular displacement, you have angular velocity, and then you have angular acceleration. Same definition is the second derivative of angle. Just plug it in there. And just rearrange this one more time. Now you feel comfortable with this, I think. There you go. Does it look good?
Okay. Okay.
How does it look? Well, John, that looks good, except that's annoying sine theta again. But then you already learned from the simple pendulum that as long as your theta is small, you can do the approximation there. Oh, that's not multiplying. Sorry, guys. It's supposed to be multiplying. There you go. All right. So as long as your angle is small, you can approximate this one to be just an mgd over I theta. And what do you see? Like, what is the limit? Okay, the limit is like when theta is small. Right there. Let's say first 10 degree, let's say. As long as your oscillation is somewhere around 10, 15 degree, the error is within like percent, acceptable. Okay, so that's when you have a small theta. Cool. All right, so with that, then you get this star equation down here again that looks exactly just like what we had before. So what you can tell is what is going to be your frequency of oscillation is going to be whatever the factor that shows up in the front. This factor right here will give you the omega square. And that allow you to evaluate the frequency of your oscillation. Is going to be equal to the square root mgd over I. You are done.
Okay.
And I can even tell you the solution of this one. You don't have to think anymore. It look exactly the same. Sine or cosine you pick, omega t plus phi. That's it, guys. Nothing new.
Okay.
Nice. So I hope by looking at these three systems, okay, and you do some comparisons over here, you see why it works. The reason it works because mathematics are exactly the same. Solution must also be the same. Okay, except, all right, now we know the connections between each omega depends on the type of the system, but you know how to figure out the omega. Once you know omega, you know the frequency F, you know the period of motion T, everything is done. Okay. Any questions so far? Cool. No question means very good.
Okay.
All right. If this is good, then the last stuff that I want to sort of give you, you know, some additional stuff that we can talk about, it's going to be simple now because you know everything. Remember, you know everything. So let's get back to the mass on spring system a little bit. And if I want to ask you, like, you know, some aspect about energy, let's say, Ajahn, what about energy? Okay. So if you want to talk about energy, there are only two types of energy in mass on spring. It's either kinetic energy or potential energy. Yeah. All right. So if you have either one of these two, and everyone knows how to figure out the kinetic energy is 1/2 mv square, you know the potential energy is 1/2 kx square. And you can see that I know exactly what x should be. And I know exactly what the v should be, right? You just slide back a couple of pages here. See, I know exactly what are the x's at any time. I know what the first derivative of that x will give me the velocity. Oh, it's kind of slow here. Okay. So you know exactly what the x should be. You know exactly the derivative of that give you the v. You just take this expression and this expression and plug it in there. You will be able to evaluate the total energy of the system at any particular time. See, that's how simple things are gonna get. Because here, just plug in that a sine omega t plus phi with the omega in the front and square them. You're gonna get omega square, a square, sine square. Cool. Plug in that a cosine omega t plus phi. You're gonna get a square cosine square. Cool. And the total energy of the system will be just a summation of the two. You just take the kinetic energy plus the potential energy. But then that's allow you to do some analysis right here. Do you see something here? See that? If you look at the analysis over here, it's just gonna be, oh, John, that's nice. Because you see that you have like a sine square over here. You have a cosine square over there. And if you can manipulate that omega and k and the m to make things sort of like, you know, like a common factor there, which you can, you know already that omega is square root k over m, or omega square is just k over m. So it turns out that omega square is just k over m. So this one just k over m, and m just cancel. Oh, so actually that factor in the front is the same thing as the 1/2 k over here that I can pull out to the front. So I just drag everything to the front, 1/2 ka square. What I have left inside is just the sine square plus cosine square. And I think everyone remember this identity. It's gonna be equal to 1, yeah?
Okay.
And that's it, guys. But that's it telling you. It's telling you that, of course, it's a conservation of energy. You have a spring with the mass, right? And then, of course, initially, you're going to have to extend this one out to some displacement A. So at that time, you're already collecting your potential energy, 1/2 ka square. Yeah, it's right there. And once you let it go, part of that potential energy will get converted into kinetic energy. And now you have to see that, all right, you start with maximum kinetic potential energy, minimum kind of maximum potential energy, minimum, which is zero kinetic energy. And once you let it go, part of that potential will turn into kinetic, and you're going to have the oscillation between the energy back and forth. Potential to kinetic energy, kinetic energy back to potential, potential back to the kinetic energy, on and on. It's an oscillation of the energy as well. See? And that orange function right there, it's just here. And that blue curve right there, that is just here. It's a sine square and a cosine square function. It's oscillating back and forth. You are done. Isn't that cool? All right. So that's kind of like, that's the neat thing about this whole thing. It's just like what you're saying over here is just once you know everything about the solution of the whole, grand, I don't know what grand is, but it's just like once you know x is as a function of time, everything is done, it's completed, right? You will be able to tell you'll be able to tell everything about that system. You know the velocity, acceleration, energy, everything, they're all good. Cool. All right. So this is a grand conclusion over here. So you get the oscillation of both the displacements, the velocity, acceleration, and energy. And no matter what you're saying, everything has to go under conservation of energy. You start your total energy of the system with that 1/2 Ka squared. So there's nowhere else to go. It's just the exchange. It's not, what's the word for that one? It's just transformation, right? From one type of energy to the other, and back and forth, back and forth. That is the simple harmonic motion, guys. Cool. All right. So the last portion of this lecture, if you don't have anything to worry too much about the quantitative analysis anymore, as you can see, there's no numerical calculation here, but we have a lot of analytical stuff that we have done. So the last part over here is just like cool down. And just so you know, that as some, application or something that's kind of nice and cool that's happening in this oscillation business over here. So it turns out, Jan, to be realistic, in reality, the oscillation should happen under like friction. So if you go back to the mass on spring, the floor is supposed to give you some friction. So what happens if we add that on? So what you can do is actually what you can introduce into your system is just introducing the friction. But there is some sort of like not so interesting if it's just introducing the friction into your system. When I say not so interesting, because of what? Because of this. All right, let's wait for the screen to refresh a bit. I'm getting a new internet pretty soon, I hope. I don't know. It's just so slow. All right, so let's say over here, if you have the friction on the floor, well done, just to be real, just add friction to it. But everyone knows to calculate the friction is just the product, right? It's just multiplication of the coefficient of friction and the normal force n. But it's just constants. So that means every time you have this term, you can just add this term into your equation of motion, and it will just change your second order differential equation by a little bit. But when I say by a little bit, I mean, it's not that interesting in the sense that you just add another constant into your differential equation. Okay, so it doesn't reveal any new characteristic of the solution. What is more interesting is this. What if your friction comes up in terms of the resistance to the motion? Whoa. All right.
Okay.
So instead of having just like a constant friction going on, what you are looking at, it turns out to be, let's say you have a constant resistance. Does it sound reasonable over there? Yeah. So you have like a constant resistance over there. And then what you're looking at over here is, let's say you put the mass in like a liquid, something liquid, fluid. And then that fluid will eventually sort of give the fixed resistance, let's say. Okay. And it turns out that resistance is function of velocity. Woo. Think about that. So that means what I'm talking about is, what if your resistance depending on the speed of the mass? The reason that this one is interesting because there are many scenario that you're facing with that kind of thing. So what you have over there is, for example, if you jump down from the airplane, like you do parachuting or whatever, right? When you saw it in the movie, at first, when you jump down, your speed is pretty much starting from zero, let's say, you don't feel the resistance from the air. But once you pick up your speed, you're falling down, then you're speeding up. The friction that you experience from the air is going to get larger and larger over time as well. Does that make sense? Until there'll be a point where, whatever that guy with the bad dude just, fight in midair and all this stuff. During that point, it seems like everything is already in constant speed. The reason it can reach that constant speed, or you can name it like a terminal velocity there, it's because your resistance from the air is already offset the weight that you're falling down. So your net force acting on you is zero. So at that time, you're falling down with a very close to constant speed. Yeah, makes sense? So it will be nice to introduce this kind of resistance, is the resistance that is velocity dependent. And the good thing about this one is the velocity is the first order derivative of x. And that term will pop up in there. So this is another class of the differential equation that you learn to solve in calculus 2. Okay, so you just add this extra term in here. It's still the second order differential equation anyway. But the thing is, when you learn to solve this one, you probably do like integrating factor, blah, 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 but we don't care about that. So don't worry about the detail. The point is the solution of this will still maintain the oscillatory behavior, just like before. So of course it has to be, it's still oscillating up and down, up and down. However, by introducing this factor over here, you will get the exponential function in the front. There you go. That's the coolness of this one. When I say the coolness of this one is, you can pretty much consider what is going on in the front to be your amplitude, right? But now, with the resistance, your amplitude depends on time. Isn't that cool?
Okay.
So it's mean your amplitude is reducing in time, which makes sense. Because once this thing get oscillations, it's going to die down. It's gonna and then eventually it's gonna disappear and stop moving overall. And this mathematics take care of that behavior perfectly.
Okay.
Very nice. Okay. So if but it's a very good question. If you're asking what is B, so you can imagine the B is just your coefficient of friction. Think of it that way, or your coefficients of resistance. The larger the B means your resistance is going to get higher. So you can think of, if this is a fluid stuff, you can think of B is going to link to the viscosity. Does that make sense? So if you have like a small B, it's going to be something very light. The fluid is going to be not very viscous. Like air, for example, the B is going to be small. But then if you think about it, if you have like a large B, for example, like it could be honey, it's going to be like, super thick and all that stuff. So the movement within that fluid will be tough. All right. And once again, your question is just perfect. It's like perfect timing over here. Now, this is the interesting characteristic that I would like to conclude today's lecture with, is this. As long as the B is not that big, you should be able to observe the oscillatory behavior still. Does that make sense? All right. So that's mean, let's say you pull the mass down, let it go. It's going to oscillate up and down with the diminishing amplitude until it goes to zero. Yeah. And that is your blue case right there. So if that is the case, we're going to name this one is the underdamped oscillation. Cool. Because it's still sort of like the damping factor. Now you can think of this as like something that's trying to damp your oscillation there. The damping oscillator, it's still under oscillations, but the oscillation is sort of having smaller amplitude over time. Okay, but now look at the other side of the story. If the B is huge, so you are looking at the movement of the mass within a very viscous fluid, like honey or whatever that you can think of, like super thick fluid. So pull the mass down, let it go. It's just it just doesn't want to go anymore. It's like it's having hard time trying to reach even back to its equilibrium point. It's just like, oh my God. And that is the black curve right here. This one, it's over damp. It's too thick. Okay. So you won't be able to see the omega anymore because you don't have any oscillation right there. Okay. Even though there was a formula for you to calculate the omega, and that's the reason why I put the prime in it, because it's going to be different value of the omega relative to what you saw before. But now, no way, you're not going to see anything. Okay. But of course, everything is going to slowly approaching the equilibrium point. The nice thing is here, guys. There will be a borderline between underdamped and overdamped. So this means there will be, some, conditions that exactly split between things that going to go over from under to overdamped. And we're going to name that one is the critically damped oscillation. It's critical. I mean, critical in the sense that it's about to switch from under to over or over to under. But when you look at the rate curve, what do you see, guys? With that perfect condition right there, you can see that the system is approaching the equilibrium point very, very quickly. See that? Isn't that nice? Things just go down and try to approach the equilibrium point very quickly. It's the quickest, actually, if you think about it. The black line, the overdamped case, of course, it's going to take forever for the system to approach equilibrium. The blue, yeah, it's going to oscillate up and down before it gets to the equilibrium. But the red one is super damn fast. Yeah, does that make sense?
Okay.
And this is how engineers use this condition to design like pneumatic or, I don't know, hydraulic or whatever things that need to be damped and get back to the equilibrium point. For example, like a choke up in your car, maybe the swinging door, for example. So every time that you have your car, hit the bump or whatever, and then you want everything back to its equilibrium, it will be probably ideal for the car, the whole thing, just go back to the equilibrium point according to that rate curve. All right. If you adjust your spring constant for the choke up to be too stiff, then you're going to have to oscillation for a while before everything get back. Or if your spring constant for the choke is just like too loose, then it's just, it's just going to travel a long time and everything will take so much time before it's approaching equilibrium, for example. Does that make sense? All right. So this thing is very, very practical. And I think engineers have to somehow have some specs, some, tables that's showing you like what kind of, numbers or specification of the fluid that you use in the system that eventually going to maximize or optimize the oscillation process in the system. Sounds like fun.
Okay.
All right, but that's not our business there to imagine what's going on in the mechanical system here. We're learning physics, and that is the physics that we are going to do later. But for today, this is it, guys. It's done.
Okay.
Any questions? Cool. All right. I hope you learned something today. All right. And wait for more excitement to come. Once you understand this, next time you're going to dive into waves, and waves, it's going to double your fun. If today is already fun, next time it's going to be even more fun. All right, guys. So I'll see you again on Saturday. All right. Bye-bye. Oh, you have a question? Yeah. Okay. Go ahead. All right. So for the rest of you guys, thank you. I'll see ya.